All right, so you have a quiz on Wednesday on chapters 6 and 7. So let's start out with, are there any questions on chapter 6? We'll just start with, any questions on chapter 6? Any questions on 6 or 7? Okay. Then let's pick up where we left off. Seems like the last thing we did was the transliteration between linear and rotational motion. Okay, I got a nod. So let's take torque and explore that. And I don't know why I spelled torque with a tau in front of torque. And let's take something that all of you have probably been doing for most of your lives and analyze it. So I want to close the door over here. Let's see if we can actually capture the absolutely dynamic display you're about to see. Let's see, is the door in there? Right now it's just blurry. There we go. So we have a door. Since a force is an influence which might cause acceleration, torque is an influence which might cause angular acceleration. In other words, if I have a door sitting right there, I want to be able to close it, I will have to accelerate it. Right now it is at rest. To close it, it has to move. Therefore, there will be a change in angular velocity. Therefore, there's angular acceleration. So, how do I close the door? Push it, okay. That didn't seem to work. Any other suggestions besides pushing on it?
Push it towards the door frame.
Push it towards the door frame, all right. That didn't seem to work either. I'm willing to bet most of you haven't thought about how to open and close a door in quite a long time. Probably ever. Other suggestions? Well, this is going to be a really long class. I'll wait it out.
Rotate it inward.
Rotate it inward. What does that mean in terms of what I need to do?
I guess push on it so that it rotates inward.
All right, so how do I push on it? Let's just stick with, instead of, assume that rotation will be a result of whatever I'm going to do. How do I need to push on it? In which direction do I need to push?
To the right?
All right, so subjective, we'll get into that in just a moment. Who's right?
Well, I guess whenever you're looking at the door, you're right.
Okay, so as you look at the door to the right. All right, So we'll just start it right there. So you want me to push on it that way? Is that what you were suggesting?
Yeah.
Okay, on the door. Not just push anything to the right, I can push this
No,
on the right.
the door.
Alright. Ew, that'll do it. Is that the most efficient way of doing it?
Probably not.
What is a more efficient way of closing the door?
Pushing on the edge,
The edge over here,
the other edge.
the other, this one up here.
The furthest point from the axis it's turning.
Alright, so push on the edge over here to the right. That does seem to be much more effective. So we think about trying to cause something to have angular acceleration. There are a couple key things. First off, a force needs to be applied. And because force is a vector, the direction of that force becomes critical. And I'm off camera again, so let's see if we can. Let's see, is that? There we go. So the direction of the force matters. Where I apply the force matters. We'll label it as R. So force matters. Where force is applied matters. And the relationship between those two matters. Because I could push on the edge with the exact same magnitude of force. I could push with, say, 10 newtons of force on the edge, but that really is not particularly effective. So how do I push on the door in order to be most effective? You can express it in terms of angle, or there's other words too that you could use.
On the opposite end of attachment?
On the opposite end? Is that-
Like the opposite side of where the door is attached to the frame?
Okay, I was thinking more in terms of, all right, so we've established I'm gonna push on this side of the door. How do I push on the door on this edge in order to get maximum torque? Yeah, I can push like that.
You push it in the direction that you want it to go.
Except I want it to rotate, so that kind of gets vague. Because I want this end of the door to go that way. I mean, ultimately end up over there. Is that the most effective to push directly in that direction? Then what would be the most effective way for me to push on the door?
Parallel to the door?
Parallel?
Yeah.
So this way or that way?
Oh, to the actual door, perpendicular.
Perpendicular to the door, yes, to the actual door. An angle between F and R. All right. We have the essence of torque right here. R is known as the lever arm or moment arm. Talked before about how moment usually means that there's some rotation involved. It is a vector, thus the vector symbol right here. It is from the axis, I'll put this in quotation marks, axis of rotation to where force is applied. force at this point, I'm hoping people are comfortable enough with the word force that, it's a push or pull. So we can, of course, write this out in long words, but physicists are nothing if not attempting to write things in as few character strokes as possible. So they came up with an equation, of course. Torque is R cross F. That sums up everything we just discussed. Now, I'm assuming most of you aren't looking at that and going, "Oh, of course, say no more." So let's actually talk about what this stuff means. So from an overhead point of view, this is a door, the hinge, and I'm going to push on the door in that direction right there. I got multiplication going on, and it is a cross for a reason. There are other, in algebra and math, they have other symbols for multiplication, but this is specifically an X for a reason. This is called cross multiplication because the symbol's a cross. I guess they could have gone with X multiplication, but they didn't. R is a vector from the axis of rotation, which typically is a hinge if there is one, to where the force is applied. So that is R. Now, if they are perpendicular to each other, you just multiply to get the magnitude. So let's say that, 1.2 meters. So let's make the door 1.2 meters. The force will make 10 newtons. And so the torque, magnitude of torque, if they are perpendicular, so if perpendicular, is just 1.2 meters times 10 newtons, or 12 what?
Meter per Newton.
All right, so you said joule, and you said,
Meter divided by Newton.
ooh, not divided by.
Also multiplied by.
Yes, all right.
Right.
All right,
Yeah.
so it's not joules, even though I understand where that comes from. So first off, meters times newtons. If you're going to write it like that, if you're going to put the meters first, you need to make sure you put a dot in between the meter and the newton. Because if you do not, if you just write meter times newton, that's actually a millinewton. This is a thousandth of a newton. This is a unit of force. So this would not be an appropriate way to write it. Typically, since capital N is not it's not a prefix, capital N doesn't have any meaning in the, little m meaning milli, little c being centa, and so forth. So you could write it like that with a dot in between, or you could write it as 12 Newton meters, even though I still prefer the dot in between. That dot is optional if capital N comes first. Please don't use the lowercase n, because then it'll be nanometers. Now, joules. If we were dealing with work, so if I push with 10 newtons on a box, and it goes, so 10 Newton force on a box, and it goes 1.2 meters, the work done would be the force times the displacement. And so that would be 12 Newton meters, or 12 joules. A Newton meter is a joule when talking about work or energy. A Newton meter is not a joule when talking about torque. It is unfortunate that they're both Newton meters, but it's what we have to live with. not joules. Not joule, if dealing with torque. It is joule. It is joule. If dealing with work or energy. Recognize a key difference in the math here. When you're dealing with the dot product, we care about how much of the force is in the direction of displacement. We care about parallel, whereas with the cross product, we care about how much is perpendicular. Get rid of some of the stuff. So I take my hinge, I got my door. Again, make it 1.2 meters long. This time I'm pushing in this direction, 1.2 meters I'm push on the end here. So 10 newtons of force that way. So I have two situations here. One, I'm pushing sort of overhead view, I'm pushing that way. And in this case, I'm pushing that way. What is the magnitude of the torque in this case?
It'd still be 12?
Give me the whole thing.
12 Newton meters.
Yes, it'd still be, yes. So torque, magnitude of the torque is still 12 Newton meters. However, these are not the same situation. If I push on the door on this one side of the door, I get a different result than if I push on the other side of the door. So how do you actually differentiate? What's the difference between these two? Or how do we communicate that there's a difference between these two? Anyone have a suggestion?
Would it still be positive or would it be negative since it's going in the opposite direction?
One of them would be positive and one of them would be negative, yes. However, there is still a direction to what does positive or negative mean there? So if I had J hat like that, if this is rotating around like that, so rotating, I guess, counterclockwise, would that be positive or negative?
Positive.
Why?
Because if you do it in the quadrants, it's in the positive.
It actually is positive, given, if I define I and J like that, it is positive. I was just curious if you had some gut feeling for it. Anyone else? Oh. All right. A wheel. How would you describe the direction this thing is rotating? It's counterclockwise to me. So how would you communicate which way it's spinning so that there's no confusion? Or are you saying that I'm wrong?
Can you consider it by like degrees?
How so?
How many degrees that it moves?
Oh, that would I would, let's say it went around once, we would both agree at 360 degrees. But we do differ on the direction it's going in, because again, I would say counterclockwise, and you would say clockwise. And I guess Joanna would say not rotating at all. Is that direct, dead on? Close to it.
Well, if you put an arrow with a, like a positive sign, whichever way you put the arrow would be positive, right?
Except, how would, expand on that, how would you do that in this case?
Well, usually we put to the right as positive, and if you go by that, then that means that that would be positive because the arrow, whenever it gets to the top, is pointing to the right.
Yeah, but on the bottom it's pointing to the left. I mean, this is a serious question about how do you actually describe this stuff. Because again, math people and physics people want to express it in as few character strokes as possible. We want to somehow communicate the idea. So they came up with what is known as the right hand rule. It is not the dominant hand rule. Do we have any left-handed people in here? All right. So specifically to you, it's not the dominant hand rule. It is the right hand rule. I have a left-handed students who do figure it out with their left hand, and then they know it's the opposite. At some point, you start to get an intuitive sense of what it's going to be, and I find for the students who start out that way, they often do sort of like, the way I view it is a double negative. They'll flip one way because of the left hand, then they flip back because of their intuitive sense. So it is right hand rule. There's clearly an axis to this. An axis of rotation, the part that's not moving except for my hand shaking. That is the axle, and so your thumb becomes the axle. So the axle in this case is either pointing towards me or pointing away from me. The fingers naturally curl in some particular direction. You want your fingers to curl in the direction that this thing is spinning. So because this is spinning around like that, I'd have to put my thumb the direction of the axle and my fingers curling in the direction in which it's rotating. The thumb points in the direction of the angular velocity in this case. So it's rotating around like this. You would say the angular velocity is pointing towards the board. The angular velocity is now pointing to the back of the room. I've gotten some nods here and potential just staring. Now, here's the issue I had when I was first starting to learn this. They would say the angular velocity is towards the board, and I'm going, there's nothing moving towards the board, and this really confused me. There is nothing moving towards the board. The fact that we're saying it's towards the board is just the math people and the physics people, or probably math people agreed and the physics people went along. This is just a convention for communicating. If I say the angular velocity is towards the board, then I know the thing is spinning around like that. If the angular velocity is towards the ceiling, it's spinning around like this. It is just the shorthand notation to communicate it with as little as possible. So if I have I and J pointing like that, we now bring in the third one, K. This is known as a right-handed coordinate system. And what defines a right-handed coordinate system is I cross J equals K. In other words, when I'm doing cross products, I put my hand in the direction of the first vector, which in this case right here is to the right. I want my fingers so that they bend towards the second vector, and my thumb points in the direction of the resultant, or product. So I cross J gives me K, pointing out. Over here, there's my R. Remember, torque is R cross F. So I have my R going in that direction, my force was going up. R cross F is pointing out of the board. Which, given the way I set up I and J, out of the board is positive K. So my torque here, 12 Newton meters K. And over here, given the same coordinate system, here my torque, 1 point, oh, I did write it correctly. So 12 Newton meters in the negative K direction. Questions to hear?
So one of those is R and the one going upwards is F?
Right, because given the way I've drawn it here, my force was going up and R was going to the right. R is again from the hinge to where the force is applied. So when I pushed on the door, I applied a torque upwards. Because I applied a force in that direction, R was in that direction, so R cross F is up. Again, nothing is physically going up, it is just the math convention that if I push on the door, if I push on this side of the door, I'm going to create an upward torque. Now I'm creating a downward torque. Suppose I flipped it around. So here at R cross F, I had R going this way and F going up. And so I said R cross F gives me a vector in that direction. Suppose I did F cross R. What would the direction of the product be? That way? In the negative K direction, all right. Because I get completely opposite answers. One's the negative of the other. Commutative property doesn't hold it. In math class, they talk about it doesn't matter the order in which you multiply to get the same answer. Potentially, this is the first time you've been exposed to the order does matter. That if you multiply in the other order, if you multiply them in the reverse order, you'd get something in the opposite direction. Now there's probably the lab that you're gonna do this Friday. Now let's go through a problem, similar to what you'll see in the lab. Let's see if I can find a darker marker. Barely. Now, similar to the lab that we did in chapter 2, when we dealt with equilibrium of forces, where we had upward force equals downward force, we're now dealing with a situation where we can look at other equilibrium. So in chapter 2, we dealt with linear equilibrium. So that was chapter 2, which meant that the total force equaled 0. Now we get to throw in a new type of equilibrium called rotational equilibrium. Then we get to chapter 8. Rotational equilibrium. Sum of the torques equals 0 Newton meters. So what you were dealing with in chapter 2 in that lab, I guess it was the second lab, I think it was the second lab, that was rotational equilibrium, we just weren't talking about it. Alright, so let's say that I have a weight of this thing, so the weight is, let's say 1.5 newtons. This is being held up. I'm just gonna make up numbers here, so let's make that 0.7 newtons, and then here 0.8 newtons. So total forces up equal to total forces down. We indeed have linear equilibrium, or in everyday physics speak, you could just say it's an equilibrium. The linear is understood. Let's say it's 0.2 meters to there, and 0.9. Actually, yeah, you know what? We'll go with this. 0.9 meters to here. And this is, we'll assume, halfway across the meter stick. All right, any questions about what this is showing at the moment, from a physical point of view? All right, so let's find the torque. So if I have a meter stick being suspended by two force sensors, what is the axis of rotation? So for example, for a door, the hinge is the axis of rotation. There's a very natural spot for that. For a wheel, the axis of rotation is the axle. But for a meter stick that's just sort of sitting there, what is the axis of rotation? Someone just speculate.
Would it be the middle of